So welcome to the Swedish NLP seminar. My name is Magnus Sahlgren and I will be the moderator here today. So this is a seminar that we organize here from AI Sweden with the support of RISE. And we do this as an online and physical event. So it's a hybrid seminar. We have people and speaker today joining online. And we have two physical locations here in Stockholm at our new office at Folkungagatan 44, yes. And we also have Gothenburg with us live. And today we're going to continue talking about large language models, which those of you who have been following this seminar series, you notice this is our main interest. And we're going to continue that topic today. I'm extremely happy to have with us Sampo Pyysalo from Turku, University of Turku, who is one of our foremost experts in this in Nordic region, and I would guess Europe, and perhaps also internationally. And I'm really psyched to hear about the work that Sampo has been doing on training a large-scale Finnish GPT model on LUMI. So I think that's it, and I give the word to you, Sampo.
All right, thank you so much for the invitation, and thank you for the very generous introduction. I'll choose not to disagree with that at this point. So I hope you can see my slides, all right, and hear my voice. So I will be talking about large generative models or large causal models for Finnish as advertised. And let me just start with a brief introduction here. So I'm a research fellow at Turku. My background is in computer science, more specifically machine learning. And most of my research over the last 20 years has been on machine learning, specifically as it applies to natural language processing. So as you can probably guess, for the last 5 years or so, we've all been going pretty crazy about transformers and ever larger language models. And the Turku NLP group is a group between departments in computer science and linguistics. The group is also about 20 years old now, a bit over, and is about 25 members, I think closing on 30 at the moment with visitors and summer trainees and so on. And a major focus of the group is Finnish natural language processing, naturally, and our methodology is very much based on machine learning and, well, recently, large language models. And just to mention some of our work, you may be familiar with things we've done. So we introduced the first BERT model for Finnish in 2019 and followed that up with a study introducing BERT models for 42 languages that was building mostly just on Wikipedia text. So fairly basic models, kind of what you might consider as baselines for national or language-specific models. And what I'll be talking about today in particular is the work we've done on the Finnish GPT-3, or what we're now just calling FinGPT-3 for short. And this is a family of large causal language models for Finnish. I'll also be slightly advertising what's coming up next. So we're kind of following up on this natural extension of being able to do one of these for a specific language and building on that to create language models as well as machine translation models for all EU languages in a Horizon Europe project that we have running. You may also be familiar with the group from some of our other work. I've not been so much involved in that, but I feel I owe it to the rest of the group to mention that we were not only doing large language models. So one of the things that has been a major focus of efforts is parsing specifically for Finnish, but also generalized neural parser. The Turku neural parser system is kind of the latest iteration of this kind of work. Also, we introduced the Turku dependency tree bank, which is now just mostly known as the Universal Dependencies Finnish TDT corpus, as well as named entity recognition corpora and many others. So our work kind of splits between this kind of methodological and modeling work and resource work, both in terms of creating unannotated resources for things like language model training, as well as just manual annotation efforts to kind of fill in the gaps that it happen to exist in resources for Finnish. Yeah, excuse me. Yeah, so within language models, I don't think language models need much of an introduction in a forum such as this, but I thought I'd say just a few words before getting started in the details of what we've been doing specifically. So language models are these days in the headlines in the news, even mainstream news, practically every day. I just picked some. These are, I think, most related to GPT-4. So upon the introduction of this latest iteration of OpenAI's model, CNBC reported that their claim that it can beat 90% of humans on the SAT, the acceptance tests to colleges in the US. CNN reports that 300 million jobs could be affected by models such as this. And a New Scientist reports on what I think is actually a fascinating report by Microsoft on sparks of general artificial intelligence that they claim they detect in these models. And the graph here is showing exam results from the GPT-4 technical report. I'll just pull out one from here. They're comparing the last iteration or previous iteration GPT 3.5 performance on various human exams to GPT-4 performance. And whereas the previous generation of models was in the bottom 10%, still clearing the bar exam, so the exam for graduating lawyers, the latest model was in the top 10% of human test takers. So yeah, there's a lot of reasons why we're all kind of excited and interested in these types of models. And so just to sketch out the very broad categories of models that we might be talking about here. So what I might call pure language models like GPT-1 to 3 are simply trained to predict the next word on texts such as books and web crawls. So these texts don't have any particular structure, and hence the models may get remarkably good at predicting what types of text might appear in a book or a web page, but they're not very good at, for example, taking or reacting appropriately to instructions or participating in dialogue style interaction. And so the next steps from there were, again, taking the OpenAI models as example, models like InstructGPT that were trained with text with an instruction context response structure. So the training data might, for example, say, produce a summary of the following document as instruction, then a big document of text, and the response would need to be a summary, an accurate short summary of that text. And then the latest iteration, which is what has, I think, mostly gotten the general public very interested in this class of models are, of course, the chat or dialogue models like ChatGPT or GPT-4. And these have been trained on texts with an explicit dialogue structure and consequently can interact with people in a way that resembles human dialogue. And yeah, just to mention, I'll mostly here talk about causal models rather than, for example, bidirectional or encoder-decoder models. And yeah, where we are in Finland, where we are in the work that I'll be talking about in this presentation is just kind of the first step. So we have created a pure language model. I will talk a bit about what we hope to build on that model, but so far this is kind of the first step towards getting something like a ChatGPT for Finnish. Specifically, what we've created is a family of models following the GPT-3 recipe. So, as I'm sure many of you very well know, the original GPT-3 was an English language model that OpenAI introduced in 2020, had a very large maximum parameter count for its time, as 175 billion. They also released a set of smaller models, starting from just a bit over 100 million. These models were all pre-trained using the same process, so 300 billion tokens and all on the same data. They report they had about 600 gigabytes of data, which means that the model only saw any single document in its pre-training data exactly once. The models are usable via an API, but as for most of the large language models created by commercial entities, the model weights themselves are not available. And our model, the Finnish GPT-3, we were running 3 years behind OpenAI, so these were released earlier this year. We did manage to match all of the parameter counts, although we cheated a bit for the very largest model. But so we created monolingual models only for Finnish for up to 13 billion parameters, so the second largest of these models. And we also continued the pre-training of the multilingual Bloom model on Finnish data to create this 176 billion parameter model that understands Finnish along with the many other languages covered by the original Bloom. We followed the pre-training process of training for 300 billion tokens, even for the smaller models, which makes them massively overtrained. But we were only able to assemble 200 gigabytes of text. So we trained for multiple epochs in order to get to this point. And the big selling point of these models, other than, well, them understanding Finnish for those who are interested in the language, is that they are available for download. You can simply go to this URL or look them up in the Hugging Face hub. I'll give a brief example of generation. So what's actually generated by the model is things like you see on the left. I put this through the DeepL neural network translator, and what we get out is the Finnish version of things like, it is crucial for the future of artificial intelligence technology in Finnish that the Finnish school system provides sufficient basic skills for children and young people to use artificial intelligence, and so on. So these models can produce this kind of reasonably fluent, reasonably coherent, but mostly kind of nonsense. And yeah, they very much do their own thing. So it would be hard to tell this model, for example, to write an article critical of the impact of artificial intelligence on Finnish technology or similar. So let me next get into some of the technical and data aspects of what we did to create these models. So the key ingredients for large language models are, of course, compute. We need quite a hefty computer in order to even partially train a model at the scale of 170 billion parameters. Here, we relied on the LUMI supercomputer, so we were in a reasonably good position here. In terms of the technical implementation, the software we built on the Bloom fork of the Megatron DeepSpeed package, which was broadly state-of-the-art at the time we were started working on this. So we were reasonably confident that we would be able to succeed in terms of having the right technological solution for training at this scale. However, for data, the picture was far less clear because the data scale of data that was used in the original GPT-3 work that we were using as a template was considerably larger than we were able to put together for Finnish, or expected to at the outset at least. So we relied on the Finnish National Library, multiple web crawls, news archives, social media, and many others. But it was not entirely clear that this was going to be enough. And yes, so you might say Finnish, unlike Swedish, is a small language with few friends. So we can't rely on data that we can bring in from close neighboring languages that might support learning our language because, well, we don't really have many. So the big question for the preparation of the project was where to find the data. And these are now somewhat dated compute optimality estimates. So people recently, the trend is, of course, to train for longer on smaller models rather than what was estimated still in 22, where this estimate is from. But this is the estimate we were building on. And if we looked at where we were in terms of compute, so how many floating point operations would we be able to invest into training this model, we would have been able to get to the tens of billions of a parameter scale. But if we looked at what we could put together in terms of data, we were just breaking a few billion parameters. So these were kind of the limits we had in terms of our computation and our data. And the data was a much harder limit than the compute. So what we did to figure out how we might be able to stretch the data that we were able to put together is, this is a graph of loss curves from kind of an overfitting experiment. So the green shows if we just have 1.4 epochs on our data, the last of the U-shaped curves shows what happens if we ran 1400 epochs on a subset of the data for the same amount of training input. And so what we find, which was very encouraging for us and which has been since confirmed in other studies, is that if we do something like 4 epochs over our data, we get no negative impact on the final loss of the model. So the model doesn't suffer from overfitting, even though it basically reads the same material 4 times. Even at 14 times, we don't get as low in terms of loss, but there's no clear overfitting. That is, the model's loss does not start to get higher. So the model doesn't get worse, even as if it does 10 repetitions over the same training data. At 40 times, it starts to definitely overfit. At 100 times or more, it is definitely not a good idea to try to stretch your data that far. But this is actually more than enough for us. So at the scale of the data that we have, if we consider, for example, that we allow the model training process to do 10 repetitions over the comparatively small training data that we have, we can kind of multiply these estimates by 10. So now if we look at where does our training data put us, we can safely estimate that we're probably able to train a model in the 10 billion parameter scale, both in terms of the data and the compute. And a few words about the specific data sets we gathered. So this shows we did a bit of weighing of the data in order to emphasize what we believed were higher quality resources. So we put a bit of a higher weight on, for example, our own internet crawl, which we had previously carefully filtered for other language modeling work. And we put a higher weight, a slightly higher weight, for example, on the National Library resources. And so this shows proportion of the total data set. So we had 3 different web crawls: common crawl, our own crawl, targeted crawl of Finnish text, and our own filtering of common crawl. So this actually introduces some overlap. The MC4 is an older common crawl based resource introduced by Google. We had National Library resources, in total representing something like 10% of the overall training data. We had social media. Suomi24 is the largest web-based social media forum in Finland. Reddit is just the slice of Reddit that happens to be in Finnish. We had a couple of open resources. Sadly, these don't represent a very large chunk of our overall data set, but we had the Finnish Wikipedia, as well as the Lönnrot corpus, which is kind of a Finnish sister project to Project Gutenberg, which collects old out of copyright books in an electronic format. And finally, we had the archives of the Finnish National Broadcasting Corporation and the major Finnish newswire service. So there are a number of known issues related to gathering data for training in this way. And these are the things we did to address, or at least mitigate those issues. So it's reasonably well established that these models can suffer from memorization, or they can definitely memorize their data, and that can lead to adverse effects in a number of applications. So we did 2 sets of deduplication to avoid having overlap between the resources, as well as duplication within an individual resource that might lead to a high number of repetitions. So we first did hash-based deduplication for entire documents. So taking out documents that were completely identical, which is something that you get a ton of, for example, in Common Crawl, because they will crawl the same site in different years and at different types. And we also did paragraph level deduplication based on n-gram overlap. Another issue frequently associated with pure language models in particular, so models that haven't been specifically aligned for human interaction, is that they have a tendency to generate toxic text for various definitions of toxicity. So for this, we created a custom classifier that we trained on a machine translated version of the Jigsaw toxicity corpus. So this corpus has, I think, 6 or 7 labels, such as just general toxicity, threats, obscenity, and so on. So we tried to take most of this sort of stuff away from the web crawl portions of our data. And finally, for personal data, so we're operating within the EU on EU data. We don't want the model to, even if it were to memorize, we don't want to give it the opportunity to memorize somebody's social security number or their home address. So we applied a series of high recall, regular expression-based and rule-based approaches to remove potentially identifying numbers, addresses, and the like. And yes, whenever I talk about this, I feel obligated to advertise LUMI. CSC, the Finnish High Performance Computing Center, has been very generous with their allocation of this wonderful system. So LUMI is the fastest supercomputer in Europe, and I think still the 3rd in the world. It's about to lose one of those titles, I believe. It has 2,500 and a bit GPU nodes. So what you see in the system, if you're using it, is in fact as many as 20,000 GPUs or graphics computing dice, because these devices have kind of two on board each device. It's a pre-exascale system, specifically about half. And you can get large allocations on this system, so in the millions of GPU hours, both via Euro HPC and national organizations like the ones we have in the Nordic countries. Very, very nice system for this type of work. Let me next say a few words about the evaluation of the models that we produced. So first of all, we, of course, observe validation loss. So we set apart a small fraction of our pre-training data, and we observe how the model loss on this data behaves over its 300 billion steps. And this shows the models from the small, about 100 million parameters, up to the 13 billion. Shows the losses throughout their training on the 300 billion tokens. So we're definitely starting to plateau for some of these, but I'm happy to observe that excepting for a tiny blip before 150 billion parameters for the 8 billion parameter model, which I cannot explain in any way. Other than those, loss tends to be monotonically decreasing throughout the training. So the parameterization, the basic training process, and all of this seems to have worked out mostly as intended. We have a separate loss curve, kind of quite a bit noisier for the very largest model. So this is taking the OpenBlue model and training it for an additional approximately 45 billion tokens with a mix of the original training data so that it doesn't forget what it already knew, and the finished training data. And because this was done during a pilot project on LUMI, there's a couple of gaps in this log from where the system just crashed and we were moving between different numbers of nodes to get this done within the somewhat short time that was allotted to us. But also for this model, we did succeed in bringing it down to the level of loss that the original Blue model showed on its original training data. So when adding in Finnish, naturally the loss of the model on this validation data that has the same balance as the training goes up, because it's never seen Finnish before, but we were happy to observe that it seems to have learned Finnish approximately as well as it learned the other parts of its training data. Of course, the losses don't tell the full story. Actually, indeed, they tell only a very small part of the story. And so we've also been developing various evaluation data sets. So for zero and few shot evaluation, which was kind of the most exciting new emergent capability that was associated with the GPT-3 models in particular, we created a small subset Finnish version of the Big Bench benchmark, which is a kind of backronym from Beyond the Imitation Game, or basically Beyond the Turing Test. So this is a very large collection of tasks, such as these illustrated here. So these show multiple choice tasks. You might have an input to the model, how many elephants can fit in a freezer, a number of options as to what the answer might be, and then the model is expected to pick one of those as the most likely. And the original data set is very large. We only translated or created a Finnish version for a small subset of that. And our process was, we started from the original Big Bench data. We put that through a machine translation service. Then we manually examined, and when necessary, corrected every single one of the translated outputs. And in this way, we created this data set. And we evaluated, as in the original GPT-3 work and in the Big Bench evaluation system, we evaluated in a range of settings from 0 shot, where the model doesn't get any examples of correct answers in its input, up to 3 shot, where the question and expected answer is preceded by 3 correct pairs of input and output. And we find largely the type of pattern that we expect. So if you give the model some examples, its performance here, average accuracy, goes up a bit, as well as larger models tend to be better at this, regardless of whether they're given examples or not. So the 0 shot performance of the larger models clearly exceeds the 3 shot performance of the smaller ones. We also looked at toxicity, mostly just as a sanity check to see if we had succeeded in bringing down the tendency of the model to produce toxic text without specific prompting. So we compare here to a previously released GPT-2 family model by a different Finnish researcher. So I'll let that model remain anonymous. We find that if we just give the model as prompt the end of text token, so basically tell the model that, okay, a document just ended, what might the next document look like? So this is kind of an spontaneous generation without a specific prompt to guide the model in a particular direction. We find that in this type of evaluation, we managed to cut the toxicity of the model to about half of what this previous generation model had. So the model will still tend to, well, mostly swear in about 2% of its generations, but this is something we hope to further weed out of the model in upcoming alignment and discussion and instruction work. Finally, bias. So this is a big topic, and the topic of quite a lot of discussion recently, and yeah, very important discussion, of course. But regrettably here, we couldn't do more than confirm that the model exhibits the same tendencies to repeat and in some cases exaggerate biases found in its pre-training data. So this small plot here shows part of our experiment on gender occupation associations. So if we look at occupation statistics in Finland, which only capture male or female, and we look at what the model predicts might be the names of people in those occupations, the model does largely reflect or repeat the biases that are found in the occupation statistics. And yes, in some cases, it predicts software engineering to be even more male-dominated than it is in reality. So this is something where we don't have clear solutions, and unless I've missed some very significant research, I think nobody else really has one either, but it's obviously something we have to be aware of in terms of how these models might be applied. So obviously you don't want a model making hiring decisions or contributing to them if it thinks that a person's name is a strong indicator of their suitability for a particular job. So this is a pure language model, and this is a question that many of us, I think, were asking before the advent of instruction following and chat-based models. What can you do with one of these things? So you have a huge model, and you've invested enormous compute into creating it. Now what can you do with it? And of course, the natural thing that comes out of a pure language model is infinite fluent nonsense. I'm not translating this one, but there's no point to it. It's just a kind of, again, a semi-coherent, mostly grammatically correct story about, well, a kind of fairy tale starting. So that's kind of the default mode of operation of these models, but not very interesting on its own. Another one I touched on already, which starts to approach a kind of something more useful, is prediction. So these models exhibit some capabilities to do more or less any task if you prompt them correctly and get reasonably lucky. So what you do is you give the model here, for example, in a one-shot setting, you give the model an example of a correct input-output, then you give it the actual question that you're interested, and you hope the model will provide the correct answer, and then the model will generate some nonsense because it doesn't know where to stop. But this is an interesting, in particular, it's a very interesting capability from a research perspective, but it is also something that with careful prompting and a good understanding of the limitations of these models, this is a way that the models can definitely do some natural language tasks to a degree. And of course, what's most exciting about having a completely open model is you can fine-tune it. So this is just showing an example of how comparatively simple it is to do this with Hugging Face tooling. There's now excellent software library support for doing, well, almost anything with models of these types. But you can load this model and fine-tune it on your data in just a few lines of code. And this has, of course, enormous potential. This is having access to the full weights, being able to modify the model however you like, is what allows all of these kind of derivative or downstream applications like instruction following or chat. And of course, we use it for research. I would say that these models, being the first big language models for Finnish, I would expect them to mostly serve as in their use for research. We hope to build something useful on top, but it is, of course, the ability to have this model in the first place for a language that allows all of the things I've been talking about. And yeah, finally, I would like to conclude with a couple of words on what's next. So where are we going from here? So at the start, I showed you these three kind of broad categories. We now have a pure language model. This places us kind of in the 2020s in terms of where the major commercial actors were in their English models. And what's followed since include these instruction tune models as well as chat or dialogue models. And these are a major focus of our current work. So for instruction following, there were at the outset no instruction data sets for Finnish available that we could just take and start fine-tuning on. So we've been creating these resources using two primary data sources. The first is kind of a mirror of our approach for the Big Bench evaluation data creation. So we take English data sets like natural instructions, we put them through a machine translation system, and then we do moderate human curation. These data sets tend to be pretty big, so we are taking small subsets and we are doing fairly lightweight curation, so rather selection of good parts than fully fixing everything that is found in the originals. And another major source is we're taking all of the corpora we've developed over the last 20 years for tasks such as parsing, named entity recognition, sentiment detection, paraphrasing, and so on. And we're just recasting these into an instruction format. So this is actually how many of the English instruction datasets came to be in the first place at such an incredibly rapid rate. It wasn't that people were creating them from scratch as new resources specifically to have models follow instructions, but rather they took existing datasets reflecting existing tasks within NLP and just recast those into this instruction format. We're also working towards being able to bootstrap instruction generation with our models. So this is the idea of resources such as unnatural instructions for English, where the instructions are in fact generated by, well, mostly a stronger model than the one you are training. We're not there yet. We can generate some prompts, but our answers are mostly hallucinatory. So they are like reasonable responses, but factually have very little to do on average with the answer that would correspond to reality. And we're also thinking, of course, about RLHF, so reinforcement learning from human feedback, which was one of the components of the Instruct GPT model, but haven't gotten around to doing any data work or modeling training for that yet. For chat or dialogue, which is, I guess, the perhaps the most exciting application from a number of perspectives. Again, there aren't any dialogue data sets that we could just download for Finnish and start training on directly. So we are, again, creating them. We have, again, 2 data sources, although only one of them is the same. So we are, again, doing machine translation followed by human curation of English datasets, here in particular, the Open Assistant dataset. And we're also starting a crowdsourcing effort using the Open Assistant tooling. So the slide here shows just an example. I'm not sure if it's readable, but it's basically a tool, an online tool that anyone can register to using their email, and they can kind of play this game of answering as the assistant, answering as human, or ranking other people's responses. And this is a tool that the Open Assistant project used to gather tens of thousands of full usable conversations for training their agent. So very nice piece of software. Of course, we don't expect to get anywhere that scale of input from the Finnish public or the Finnish speaking public, but we're optimistic that we can at least make a start using this sort of crowdsourcing effort. So this is still very early. We don't have anything to share in terms of like an URL. It's just in internal testing now. And finally, as I alluded to at the beginning, a next step is models for all EU languages. So we're one of the partners in the High Performance Language Technologies project, now just past its first 6 months, which includes the goal of creating language models as well as machine translation models that cover all of the EU languages, as well as quite a few others. The project will be creating causal, bidirectional, as well as encoder-decoder models for all of these languages. And luckily, this doesn't all fall on us. There's 8 partners in the consortium. So in Turku, we're currently just focused on causal language models. So quite a lot of it is just applying what we learned in creating these Finnish GPT-3-like models and adapting that to other languages. The project is scheduled to perform an initial data release and first models this autumn. Don't expect those to be very good yet. So this is still just the early stages of a 3-year project, but we will be providing some look into what sorts of things we're creating. The project is very open to collaboration, and we would be very happy if you were to get in touch. We do have a website here. I'm sure we can make these slides hopefully available somewhere, so you don't have to remember hplt-project.org, but perhaps you can grab it from there if you're interested in learning more. And with that, I will conclude with my thanks and acknowledgements. So a really big facilitator of this sort of work was the National Library of Finland, with whom we had a very nice collaboration. We also received extensive technical support. So none of us started out as supercomputer experts like at the outset of this project. None of us had done training at this scale when we were starting to work on this project. So we got extensive technical support, both from the LUMI user support as well as CSC, the National High Performance Computing Center. We also worked with Hugging Face, who were very generous with their time, supporting us in particular in adapting Bloom as well as their software stack for this. At AMD, we had an excellent contact with Samuel, who contributed a lot to getting this thing run efficiently. And yes, for compute, we like to thank LUMI for funding mostly EU HPLT. All right, thank you. That's all I have for you today. And I hope I can hand over to you and perhaps answer some questions next.